people are very smart. So we have some good way to eliminate spatial chirp. Another challenge is, can we create up chirp by a grating pair? In theory, it's not possible because angular dispersion always gives you anomalous dispersion, right? So always down chirp. But some scientist is very smart. He proposed this way, 4F configuration, or usually referred as Martinez compressor, because this is the inventor. He invented this scheme. Okay. So at the first glance, this is very different from the traditional grating pair that we have seen. Right? Traditionally, the two gratings are in parallel with each other. But here, in addition to two gratings, the second one will be shown later. Okay? There are two lenses, L1 and L2. Okay? And the geometry is like this. This is your instance beam striking the first grating, G1, and angular dispersion, so different colors spread onto different directions. And the purpose of lens here, L1, is to focus, okay? Focus the Gaussian beams, okay? Remember, each color represents one Gaussian beam. And you know if your Gaussian beam hits the lens and the separation is one focal length, what happens? After another focal length, the Gaussian beam will be focused onto a very small spot. Okay? And in this way, you can see different colors will be focused onto different small spots along this focal plane. Okay? Then you repeat the configuration. Another F, another length, another, here you have a small spot. So after one focal length, becoming collimated beam, right? So at position A prime, everything comes back. Everything comes back. Okay? So you can regard point A is imaged onto point A prime. A and A prime are essentially the same. Okay? Any question? Oh, that's why it's called 4F configuration, right? From first grating to first length, 1F. From first length to second length, 2F. And there is a focal plane in between. From second length to second grating, ideally another F, so you have 4F. And the purpose is to image point A onto point A prime. Okay? Then, if you place the second grating G2 here, okay, then traditionally we say the definition of small b is the distance from the first grating to the second grating of the reference ray, right? So in theory, it should refer to from point A to point B. That's the definition of small b. But because of the imaging, small b becomes from point A prime to point B under the 4F configuration. Okay? So B becomes A prime B, or I use another symbol L2 here. Okay. So if your grating G2 is placed here, L2 equals 0. Nothing happens. It's just like a telescope. Okay. But if you displace your second grating by L2, something happens, you see. This is very similar to the traditional grating pair. From first grating to second grating in parallel, the two gratings are in parallel. Okay? So if L2 is like this, a positive number, the second grating is behind A prime, nothing new. You go back to the traditional grating pair. Okay? But now you are able to create negative L2 or a negative B. If you have negative B, your formula shows you will create normal dispersion. Okay? So that means you have to place the second grating maybe here. Then you got normal dispersion or upchurp. Okay? Any question? So this is something some particular way you can create normal dispersion by grating pair, but not just grating pair. You need two lenses, extra lenses. Okay. When do you need to create normal dispersion? If you don't need, this is useless. In what occasion you need to create normal dispersion or upchurp?
To solve downchurp also.
Yes. Maybe we can talk about the chirp pulse amplification maybe next year. In that case, you need to create both normal dispersion and anomalous dispersion when you try to build amplify to amplify your femtosecond pulse. Okay, so in that case, you have to create two signs, chirp of two signs, not just down chirp. You need up chirp. So maybe in one occasion you need something like this. In other occasion you can use traditional grating pair. Then you can fulfill the requirements. Another interesting thing is if you place the grating G2 here, supposedly nothing happens. But if you do something here, what can you do? This is a very ideal place because different colors are focused onto different small spots. So maybe you can place an array of modulators here, performing amplitude and phase modulation color by color. Then you can do pulse shaping. Because in that way, you can manipulate the spectral amplitude and the spectral phase, essentially arbitrary, right? Not just quadratic phase, you can arbitrary phase. Just controlling the modulation pattern here. So that's the pulse shaper, Fourier pulse shaper. Okay. So 4F configuration is very useful in ultrafast optics. Okay. Now the last section, chirp the mirrors. Maybe you need to review some fundamental optics. So I will talk about distributed Bragg reflectors first, DBR, then simple chirped mirrors and the double chirped mirrors, okay, SCMs, DCMs. And the purpose of chirp mirrors is to compress the pulse, just like the grating pair. Okay, some mathematics. Consider one-layer dielectric film. Maybe you studied this subject in optics before, right? You have 3 layers actually. Ni usually is air. N1 is a film of thickness D1 of index N1. And the Ns is the substrate. Suppose the thickness is infinite, okay? So Ni is infinite, semi-infinite. N1 is finite of thickness D1. Ns is semi-infinite as well. So 3-layer structure. And if you do normal instance, okay, you shine a laser beam normally, okay, and you can draw the electric field in red color, magnetic field in green color, and the wave vector in blue color. Okay, following the right-hand rule, right? 你的电场打叉是向内就是 x，OK， 磁场向右是 y x y z，right？ 横直的方向就是你前进的方向，就是 wave vector 的方向。这个就叫做 incidence beam。Okay, so every subscript is I incidence. 这个 beam 打到 first interface. Okay, between Ni and N1, there is partial reflection and partial transmission. You know that. For reflection part, you have reflected electric field, also in x direction. Your refractive magnetic field in minus y direction, such that your propagation direction is along minus z direction because of the reflection. Okay, and for the time being, we skip what happens inside the film. Just look at what happens in the substrate. Partial transmission, right? So your propagation direction is kt along the positive z direction. Your electric field is still in x direction, and your magnetic field should be in y direction. Still the right-hand rule. Okay? Any question about this picture? Okay. So the electric field, I means incidence, R means reflection, T means transmission. 所以你有入射电场、反射电场、穿透电场，你有3个电场 ，OK， 都在 x 方向。那 magnitude， 叫 amplitude， 叫 EI、ER、ET，but EI、ER、ET are phasors. They are complex numbers, not real numbers. Okay, amplitude and phase. You have wave vectors Ki, Kt, incidence and the transmission along positive z direction. And the wave numbers are Ni times K0 or Ns times K0. Index times wave number in vacuum, K0, 2 pi over lambda 0. Okay? But your refraction wave vector is in minus z direction. Magnitude is Ni times K0 because refracted beam is in the upper layer here. The index is Ni, so the formula. Then we need some electromagnetics, Maxwell's equation, right? If you have electric field and the wave vectors, can you calculate magnetic fields? I show you incidence magnetic field, Hi, vector equals z unit vector cross Ei, the vector phasor of incidence electric field, divided by eta I, the wave impedance in the first layer here. Okay. But why is that? Why you can use this formula to calculate magnetic field? Do you know that? 还记得吗？怎么用电场去算磁场？ Carrier-free Maxwell's equation. You have 4 equations. Which one?
The last two with curl lines.
Curl E or curl H? Both? Maybe you just need curl E equation. Curl E equals minus partial B over partial T, right? But time derivative is replaced by j omega in the frequency domain. This is in frequency domain, okay? And the B becomes mu times H, okay? But you need a curl operation, right? There is no curl here. This is closed, not curl. Outer product, right? So what happens? remember here we are using plane wave model, right? That's why you have wave vector. Each plane wave corresponds to a unique wave vector. And under the wave vector model, the curl operation becomes an outer product operation with respect to k vector. That's why. That's the only reason. Okay. So anyway, it comes from the Maxwell's equation. And if you substitute EI by this one, you can have this relation. For the same reason, you can calculate HR, reflected magnetic field, as well as HT, the transmitted magnetic field, based on corresponding electric fields and the wave vectors. And I also introduced some new relation here. For example, by formula, you should use ER, reflected electric field. But if you define reflection coefficient small r, ER equals R times EI because of the definition. Okay? Reflection coefficient is defined by the ratio of ER to EI. 就是反射电场的 phasor 除上入射电场的 phasor 这样的一个 complex number 叫做 reflection coefficient. If you define that, ER becomes R times EI. For the same reason, ET, transmitted electric field phasor, becomes transmission coefficient small t times instance electric field phasor, EI. Okay? So you have all these equations. Too complicated? We can speed up. Boundary conditions. Okay. Boundary conditions require that the total tangential fields are continuous, right? Let's go back to the geometry here. What is the boundary condition you have to use? You have two interfaces, right? Interface 1, interface 2. In either case, say interface 1, the total electric field, but only tangential component. 切线方向才算. Okay? But our electric fields are in x direction, so it's tangential anyway. 在这个 interface 上面的切线方向总电场要跟下面的切线方向总电场相等，这叫连续。OK， 磁场也要连续。然后第二个界面也是一样，这叫做 boundary conditions. So you have 4 boundary conditions here. Okay. The problem is now the total fields slightly above interface 1 is easy, right? What is the total electric field slightly above interface 1? You just have 2, right? EI plus ER, that's it. But so far it's unclear what is the total electric field slightly beneath interface 1, right? And for the same reason, it's easy for total electric field slightly below interface 2, but it's unclear for total fields above interface 2. Okay? So what do you have to perform to get those missing total fields? Of course, it comes from the contribution of this layer, N1 layer, right? So far, we don't use any information about the N1 layer in this page. Okay. 我会跳过中间这一步，我只是要告诉你失去的环节在哪里。就是你必须考虑呢，这边的电场跟磁场会继续 propagate。而且呢，这有2个 interface， 就有点像个什么 cavity， 来回 interference。OK， 把这件事考虑进去，你才能算这里的 total fields. Then performing boundary conditions. If you do that, you can have the you can have a matrix equation relating E1H1 with E2H2 by a 2 by 2 matrix M1. The 4 elements are shown here, where you just need 2 parameters from N1 there. Delta 1, which is 2 pi times N1 index times D1 thickness normalized to working wavelength. Apparently, this is something about phase shift. Is it okay? Why it is about phase shift? You see 2 pi over lambda 0, that is K0, wave number. Wave number times path length, N1 D1 means path length. Wave number times path length means phase shift. So what's phase shift here? Delta 1. It means the phase shift for your plane wave from here to here. 就为了通过这个 layer 1所要经历的 phase shift 叫做 delta 1. Okay? The other parameter is Y1, which is index N1 over wave impedance in vacuum, eta 0, and usually is referred to admittance of N1 layer. You just need these 2 parameters. Delta 1, Y1, you can obtain this 2 by 2 matrix. And the matrix is used in relating E1H1 means here, total electric field and the total magnetic field on the first interface. E2H2 means total electric field and the total magnetic field on the second interface. 好，所以这个矩阵的用途是让这2个界面上的总电场、总时场的关系建立起来，这就是 2 by 2 matrix. Okay. Then substitute E1 total electric field on interface 1, as you just mentioned, it's EI plus ER, but ER equals R times EI, so you have 1 plus R parentheses times EI. That's your total electric field on interface 1. For the same reason, you can calculate total magnetic field on interface 1. Total electric field on interface 2 is easy, just 1 term, transmitted electric field. Only 1 term for transmitted magnetic field. Okay? 如果把它带到这个 matrix equation, you can have equation 17, the formula about your reflection coefficient. You have a closed form relation. 好，你的意思是这个3层结构呢，最后等效的这个反射系数公式就全部决定了。你只要知道 parameter delta 1, y1 还有所有的 index， 你就可以用 equation 17直接算出反射系数，而且这是一个 complex number. Okay. Of course, you can derive the formula for the transmitted coefficient, T, but here we do not need that formula.